Matrix multiplication can be weird. But what if it acted like a number? For example, take minus 5, 6, minus 3, 4 times the vector 2, 1. Multiply and simplify, and we end up with minus 2 times the original vector. So this matrix just acted like a scalar multiple. Let's try with a different vector. How about 1, 1? This time, we don't get minus 2, we just get 1. Again, the matrix acts like a scalar, just a different scalar for this vector. One more, how about 1, 2? This time the result is not a scalar multiple. It's not even close. The vectors 2, 1 and 1, 1 are special. They are eigenvectors of this matrix. Eigen is the German word for same. Eigen is the German word for own. It's the matrix's own vector. The minus 2 and minus 1 are eigenvalues. These belong specifically to their vectors or any scalar multiple of that vector. This raises the question, how do you find an eigenvalue? An eigenvalue lambda is any scalar so that AV is equal to lambda V. In other words, the matrix acts like lambda. It's always easier to solve an equation equals 0. Now we can factor out the V. The lambda needs to become a matrix, that's why it gets the identity matrix. This equation says that the matrix A minus lambda I is not invertible. That means we need to find all the lambdas so that this matrix is not invertible. The easiest way to do this is to solve the determinant equals 0. This determinant has a name. It's the characteristic polynomial. It'll always be a polynomial in lambda. How about an example? Use the same matrix from before and find the eigenvalues. Set up the determinant, expand, simplify, and factor. This is the characteristic polynomial of the matrix A. We can solve this equals 0, and our eigenvalues are 1 and minus 2. This shouldn't be surprising as we saw it previously. Notice, a 2 by 2 matrix has 2 eigenvalues. Isn't that interesting? You should ask yourselves how many eigenvalues an n by n matrix has, and then try to justify your thoughts. We found the eigenvalues. How about the eigenvectors? Go back to this equation. In this, V is an eigenvector of A. Notice that V lives in the null space of the matrix A minus lambda. And that's exactly what we need to find, the null space of that matrix for each eigenvalue. Step 1 to finding eigenvectors is finding eigenvalues. You always need to do that first. Continuing with the same matrix, we find the null space for each eigenvalue. Start with lambda equals 1. Then A minus I is this, which reduces to this. That means x1 equals x2, so that the vector x is x2 times 1, 1. For the eigenvalue lambda equals 2, A plus 2i is this, which reduces to this. Then the eigenvector x is x2 times 2, 1. Do these two vectors look familiar? Of course they do. They're the eigenvectors from the beginning. One thing to notice is the free variable. Any scalar multiple of 2, 1 is also going to be an eigenvector with eigenvalue of minus 2. The span of 2, 1 is called the eigenspace of lambda equals minus 2. One more example. Find the eigenvalues and eigenvectors of this matrix. This is a 3 by 3 matrix, so finding the characteristic polynomial can be a bit of a chore, but I find it to be minus lambda minus 9 times lambda minus 2 squared. Notice, lambda equals 2 has an algebraic multiplicity of 2. It's a double root. First, lambda equals 9. Set up the matrix and reduce. We find a basis of the eigenspace is 1, 1, 1. Second, lambda equals 2. Set up and reduce. The basis of the eigenspace is 1/2, 1, 0, and minus 3, 0, 1. The eigenspace has dimension 2, or geometric multiplicity 2. Any linear combination of these two vectors is also an eigenvector of A with eigenvalue 2. In general, the algebraic multiplicity is always bigger than or equal to the geometric multiplicity.